Hi guys, welcome to my all-in-one AQA new spec physics video. Just to remind you that I do an accompanying revision guide. It's a PDF with all three sciences and it's for triple students. And if you want to get hold of a copy, then you need to email me sciencewithhazel@gmail.com, and that costs £3. It's not a direct transcript of everything I'm saying, but it's incredibly similar because it just comes out of my brain and it tends to come out very similarly each time. Anyway, enough gabbling, let's get started. Let's talk about different types of energy. So be prepared to list these. So you've got sound energy, thermal energy, chemical energy, which is something that you find in things like matches and food. That's quite a weird one. Nuclear energy, electrical energy, light energy, kinetic energy, and the two types of potential energy, which is things like elastic potential energy and gravitational potential energy. They may well ask you how to convert between those different forms of energy, so they'll give you an example, something like what energy transfers take place in a mobile phone. So if you think about it, electrical energy goes into the battery, which therefore transfers that energy into chemical energy, and then when the phone's in use you get all sorts of energy. You get light energy, you get sound energy, and you probably get a bit of wasted energy as thermal energy. What about a kitchen mixer? Well, what's going in that case is electrical energy. What you're getting out of it is kinetic energy, which is the mixer turning. The wasted energy here is sound, and there does tend to always be some wasted energy in the form of sound and heat. About energy transfers in a catapult. So what you're starting with there is elastic potential energy, because that's stored inside the elastic of the catapult, and then as soon as you ping something out of it like a ball, you've got kinetic energy. So the three heat energy transfer ways you need to learn are conduction, convection and radiation. Let's start with conduction. So conduction is the transfer of heat without the substance itself moving. We know that really good conductors are metals, which makes sense because when you pick up a pan, for example, that has a metal handle, then you have to be careful you don't burn yourself, because when the pan's been on the whole thing becomes hot, so you might need to wear an oven glove, for example. The reason why metals are very good thermal conductors is because of the arrangement of the particles. First of all, they're very close together in a very regular pattern, and metals have the added advantage of having a sea of delocalized electrons, and those electrons help to transfer heat throughout the whole metal. So good conductors have close particles, and in the case of metals they have free electrons. We find that wood isn't as good a thermal conductor, and that's because it is an insulator. Now, an insulator is a poor conductor. Air is another example of a very poor conductor, and that's because the particles are very far apart, because obviously air is a gas. Therefore, when the particles vibrate, they don't actually pass on their energy to neighbouring particles particularly well. Obviously in a vacuum, so space where there's no particles, you'll find that conduction doesn't occur at all. So that's conduction done. Next up, I want to talk about convection. Now convection is a heat transfer which occurs in liquids and gases. Kids said get off the table. Jesus. What you find here, I'm going to use the radiator as an example. So the question here is, how do whole rooms become heated when a radiator is usually only found in one or two places in the room? And this is because of convection. So what happens is the radiator heats up, then the particles of air above the radiator become warm. Because they've become warm, they've gained thermal energy, they therefore gain kinetic energy, and they start vibrating more. These vibrations mean that they occupy more space, and therefore by definition they become less dense. Less dense particles are lighter, so they rise, and you end up with a space where the warm particles were originally occupying. This space needs filling, so you find that colder, denser air moves in to replace that hot air that has now moved upwards. The radiator continues to heat, so it now causes those cold air particles to be heated. They do the same thing, they vibrate more, they occupy more space, they rise, and before you know it, a convection current has been set up. Last up, we have radiation. And infrared radiation is, remember, it's one of the members of the electromagnetic spectrum, and infrared radiation is literally given off anything that is hot, and it is a wave, and that is how we feel the heat from the sun, because like I said before, space is a vacuum and yet we're all still here, and that's because we can receive heat from the sun, because the infrared radiation travels across all those millions of miles to us. You just need to know a couple of things, which is that first of all, black substances are very good absorbers of infrared radiation. Anyone with really dark hair like myself, you'll notice in the sun that it gets really hot and uncomfortable, and that's because really dark browns, black colours are good absorbers of infrared radiation. People with blonde hair, and again white things, silvery objects, they are very poor absorbers of infrared radiation. They are much better emitters. So that's something worth thinking about. I just want to bring what I've been talking about into a more realistic situation, so we're going to take a few real life examples. Things like polystyrene cups. You might have a cup of tea in there. So what would happen therefore if you added a metal spoon to that tea? Well, you would find that the tea would cool down quicker. Why? Because metal is a very good conductor, so it would draw some of that heat energy out of the tea and it would be lost into the surroundings. If you place a lid on the tea, you're going to slow down the speed at which it cools down, and that's because you're trapping a layer of insulating air between the tea surface and the lid. And we know that air is a poor conductor. It's a very good insulator because the particles are very, very far apart. And it also helps prevent convection currents being set up above the surface of the tea, which would also speed up the rates at which heat was lost. A student investigated how much energy from the sun was incident on the Earth's surface at her location. That literally means how much of the sun's energy kind of arrived on the Earth's surface, how much was projected onto it. She put an insulated pan of water in direct sunlight and measured the time it took for the temperature of the water to increase by 0.6 degrees Celsius. Wild. The apparatus she used is shown in figure 3. So we've got our incident solar radiation, the transparent lid, a thermometer, some insulation and the water. Choose the most appropriate resolution for the thermometer used by the student. The crucial thing here, she's measuring to the nearest 0.6%, so it's going to have to be a very precise thermometer, which is why 0.1 degrees Celsius is the answer, because with the other two options she couldn't actually measure 0.6 degrees. The energy transferred to the water was 1050 joules. The time taken for the water temperature to decrease by 0.6 degrees Celsius was 5 minutes. The specific heat capacity of the water was 4,200 joules kilogram Celsius. Write down the equation which links energy transferred, power and time. So it is E energy equals power times time. Calculate the mean power supplied by the sun to the water in the pan. So we've got power. Let's rearrange that equation. It looks like this, by the way, in the triangle, which we know I love. So because we're after power, we cover that up and we see the power is given by energy divided by time. So it's always good to write out your equation. And we've got our energy here. It's 1050 joules divided by time, which is 5 minutes, but that's not the SI unit of time, it's seconds, so we have to times that by 60, don't forget that. And we've got an answer here which is 3.5 watts. For part 4, calculate the mass of water the student used in her investigation. Use the correct equation from the physics equation sheet. So there's all the information at the top. We know we've got energy, we know we've got temperature, we've got time, we've got specific heat capacity. So just scan down that physics equation sheet and see which of those equations has those values in it. And you'll see that it's this one, which is delta E, so that's change in energy, equals mass, which is M, specific heat capacity, which is C, times delta theta, which means change in temperature. Don't get mega confused there. And then just substitute in the values you've been given. So you've been told the energy transferred was 1050 joules. We're looking for mass, so we're keeping that as M, times the specific heat capacity, which in the question above says it's 4,200, times it by the temperature change, which was 0.6 degrees. So how do you work that out? Well, first of all, you have to do 4,200 times 0.6 in order to sort out the right-hand side, which is 2,520 M equals 1,050. And then how do you get M by itself? Well, divide both sides by 2,520. So 1050 divided by 2520 equals 0.416 kilograms, which is the correct answer. I'm just going to make sure I round it properly. So that's actually the answer there, because I've made sure I rounded up at the end. The student's results can only be used as an estimate of the mean power of her location. Give one reason why. So where are the errors in her experiment? We could say the energy from the sun was used to also heat the pan as well as the water, or energy was lost to the surroundings. So anything sensible like that. There's always something about renewable, non-renewable energy. So non-renewable energy is things like fossil fuels, so coal, natural gas, oil. These are things which are running out. They're very good at providing us with energy, but if we carry on using them at the rate we're using them now, we're going to run out. And because they come from fossils, they are not going to be replaceable. So we're turning to renewable energy, things like solar, wind, hydroelectric, geothermal. All those sorts of things are renewable energy, and you need to be able to state the advantages and disadvantages of both. They all tend to have the same kind of disadvantages, which is that they're unreliable. So for example, if there's no wind, there'll be no wind power, no sun, no solar, no waves, no wave power. The only type of reliable energies out there are things like hydroelectric, because that's, remember, when water falls down a dam. That tends to be quite reliable unless there's been no rain. Geothermal tends to be very reliable, but remember there's only very certain places on Earth where you can harness geothermal energy. Places like Iceland, where there's a gap between the two tectonic plates. So places like in England, you won't be able to get geothermal energy. They could ask you how energy transfers occur, for example, inside a hydroelectric power station. They do like to ask you that, because remember, water gains gravitational potential energy because it's at the top of the dam. As it falls over the dam, it will gain kinetic energy transferred into electrical energy to therefore power houses. This might seem quite bitty, but I'm just literally racking my brain to think of the questions they'll ask you. They could ask you how a fossil fuel power station works. And actually any power station kind of works in the same way, which is that either if they're burning biomass or they're burning fossil fuels, what you're doing is you're heating water. That water turns into steam. The steam turns a turbine turns a generator, and a generator generates the electricity. So those are all the steps involved in generating electricity. Nuclear power is quite an interesting one because it's not technically renewable because you can't make more radioactive material. However, such tiny amounts are needed, it means that it's very unlikely to run out. So there is a huge potential for nuclear power. However, disadvantages include the fact that there's radioactive waste which needs to be stored very carefully, because if that escapes into water supplies, that could cause cancer. There are high decommissioning costs, and that means it's just very expensive taking the whole power station apart once it's been used for about 20 years or so. High startup costs obviously follow, so it's going to be expensive to make those factories in the first place. Right, so the topic of static electricity, there's actually not too much to go into with this. Just remember, when you're thinking about static electricity, it's all to do with electrons being transferred from one place to another. So, for example, a polythene rod, which is rubbed with a cloth, will become charged. Why? Because electrons will transfer themselves from the polythene cloth to the rod, so it will become negatively charged. That therefore means it attracts positively charged items, because remember, opposites attract. The questions always go the same, and they'll talk about why does it become charged, and literally the 2 marks you need to specify are, it's the transfer of electrons using friction. And if you actually look at past exam questions, you'll see what I'm talking about. That is so often the answer, I can't even explain. Why does a balloon stick to a wall? Well, you've charged it using friction. The balloon has become negatively charged due to the transfer of electrons, and then it sticks to the wall because it repels those electrons away from the wall, meaning that it can stick to the positive charges. I'm trying to think of other questions, so things like, why do your hairs stand on end when you touch a Van de Graaff generator? That's because all your hairs become negatively charged, they therefore repel, so they stand up on end. Why can't you become charged on a metal slide when you slide down it? Well, that's because metal is a good conductor. So often they'll ask you about metals, things not becoming charged. You just need to say that it's a good conductor so the electrons can freely flow. They like asking you about the uses of static electricity, so something like spraying a bike frame. The way that this works is you give the bike frame a positive charge. You can give the paint all a negative charge, which means the paint repels itself and turns into a fine mist. Then it's attracted to the positive bike frame. One of the advantages of this is, first of all, you get an amazing finish because you get paint in all those hard to reach places. Secondly, you don't waste paint. One further use of static electricity is an electrostatic precipitator, and that's what they use in factories which produce a lot of polluting smoke full of soot and dust particles. So what happens is the smoke rises through this chimney, it's given a charge, and then there are some plates that sit at the top of the chimney that the smoke and everything has to pass through, and it's given the opposite charge, meaning that all the soot and dust particles stick to the plate, allowing just the clean air to basically escape through the top of the chimney. Then they knock those plates together occasionally, causing all that dust and sediment to fall down so it can be removed and safely disposed of. They may well ask you, however, about the dangers of static electricity. So that's things like a plane becomes charged when it's flying because of friction between the clouds and the plane. So when it lands and they bring a fuel tanker nice and close in order to refill the plane, you can imagine that a spark could go from the plane to the fuel tanker and cause a massive explosion. So that's a big no-no. So what happens in this instance is the plane is given an earthing strip which is made out of metal, because then that can conduct the excess charge away from the plane to Earth, meaning that there's no risk. Remember that lightning is an example of excess charge draining from the clouds to ground, and that's a good way of adding nitrates to the soil, which is a biology topic to do with the nitrogen cycle. And it's not really a danger, but things like TV screens and computer screens end up being covered in dust because they become charged and they attract little uncharged particles of dust, meaning that the dust covers the computer. I'm just going to go straight into the different symbols used of the electrical components found within an electrical circuit. So first of all, the most straightforward ones. And I apologise. Oh my goodness, what is that? It looks like a lamp. Right, this is a cell. And what that does is it provides the push needed to drive the electrons around the circuit in order that you can light up bulbs, get motors turning, that sort of thing. Ignore the weird squiggle. I'm so sorry about that. It's terrible because it makes it look like I mean to draw that. It's not. The cell is right there. If you have more than two cells together, or two or more cells together, that makes more sense, like this, you have a battery. So just make sure you can distinguish between a cell and a battery. Next up, I'm going to draw a bulb. So that's just a circle with a cross in the middle. After that, I'm going to get slightly more complicated. I'm going to draw a resistor. So you need to draw a rectangle with two lines poking out either side. That is a resistor, and what that does is it obviously alters the resistance of a circuit, and that basically means altering how difficult it is for the electrons to flow around the circuit. If I draw a line going all the way through it, that's no longer a resistor, this is a fuse. Remember, a fuse is a safety device. You find them in plugs, and they're there to stop fires being caused if the current gets too high. If the current gets too high, the wire in the fuse melts, breaking the circuit and stopping any danger. Going back to resistors then, I'm going to draw my regular resistor again, and then this time I'm going to draw an arrow going through it. This therefore means, don't ask me why, that it is a variable resistor, and it's one that you can alter the resistance of. Just to give you a little overview, why not? If you have a resistor like this, right, if you increase the temperature of the resistor, then what you find is the resistance of the circuit increases, and the reason why is because of this. In a metal, this is also chemistry, you find that the structure is very much like this. It is positive metal ions, I'm going to put positive charges on these, in a very regular pattern surrounded by what we call a sea of delocalized electrons, which I'm calling E- because electrons are negatively charged. Now those electrons flow around the circuit carrying the current. Now if you increase the temperature, what happens is you increase the kinetic energy of the positive metal ions, and what they do is they vibrate more. Now if they vibrate more, it means that they prevent the electrons flowing around the circuit so easily, therefore increasing the resistance. So that means if you increase the temperature of a regular resistor, you find that the resistance increases because the metal ions move more and impede the flow of the electrons. Now there is an exception to this, and it's a special kind of resistor called a thermistor, which I'm drawing right now. Thermistors are unusual in that if you increase their temperature, then the resistance decreases, but it's basically because they're not made out of a regular metal, they're made out of silicon, which means they behave differently. But don't worry about that. I just want you to remember that if you increase the temperature of a thermistor, then the resistance decreases, and likewise if you decrease the temperature of a thermistor, the resistance increases. Right, I think I've said enough about that one. Now we're going to look at this version of a resistor.
Oh my god, can you please draw it in when you're doing it more circular than that, because that is horrendous. And it has a couple of arrows coming into it, and this is an LDR, which is a light dependent resistor, one which depends on light. And if you increase the light levels, then you find that resistance decreases. If you decrease the light levels, then the resistance increases. And an everyday application of this is street lights. See, like I told you, I'm just telling you little pieces of information that may or may not come up in the exam. Next up, I'm going to draw a diode, which is an arrow like this. And a diode only allows current to flow in one direction, so the direction of the arrow shows which direction that current will be flowing, and in this case it will be going from left to right, so no current can flow the other way. If you draw that with a couple of arrows coming out of it, then it's a light emitting diode, so it allows the current to flow in one direction and it emits light at the same time. Right, have I forgotten anything? The simple things like the wire just looks like that, a switch looks like this, that's an open switch. This is a closed switch, so obviously when it's open, the current can't flow because the circuit isn't complete. You have things like that, which is a voltmeter, and what that does is it measures the voltage, otherwise known as potential difference of the circuit. Make sure you're happy with interchanging between those two names, because they mean exactly the same thing, and obviously that measures in volts. Circle with an A in it is an ammeter, and that's measuring the current of the circuit, and that's also in amps. You might see a circle like this, which is just standing for motor. Have I forgotten anything? Probably, but oh well, if I can't think of it now, then it's probably not that important, she says. Right, so let's move on. I'm going to open a new page. How do I do this? I'm so slow and rubbish, sorry. Okay, new page opened. So next up, you need to know some simple circuit rules. And that is things like how you add an ammeter or a voltmeter to a circuit. So if I just draw a really simple circuit now, I'm going to just add a cell. And actually, I'm only going to add a bulb because I can't be bothered to draw anything else. So the question is, where do you add the voltmeter and the ammeter to this? So what you do is you add the ammeter in series, and what that means is you just add it to the main part of the circuit, and that's because it's measuring the current. So the flow of charge around the circuit, so you can just pop that into the main part of the circuit. Now, the voltmeter, as I said, measures the potential difference, and what that means is that it's measuring the amount of useful energy transferred to a component, and it's measuring therefore the difference in the amount of energy going into a component and the amount of energy coming out. So therefore it makes total sense to draw it in parallel, and that means as a separate branch like this. So you draw the voltmeter in parallel as a separate branch around the component that you wish to find out the voltage of. So the potential difference means the difference in energy transferred before the bulb and after it. So I'm going to pop it in a parallel circuit around the bulb like that. And if you're struggling to remember, just remember potential difference means the difference in something. So if you just popped it into series, it wouldn't be measuring the difference between anything. I hope that makes sense. And they love asking questions like, what's wrong with the circuit? And you would often see that the ammeter and the voltmeter are in the wrong place, so just make sure you're clear on these rules. And the other thing is that the flow of charge comes out of the positive terminal, which is the longer line of the cell, and flows around to the negative one, so make sure your arrows are facing this way. Cool, yeah, I'm happy with that. Okay, next up is the difference between series and parallel circuits. So if I just draw a series circuit there, and say that the light bulb is a certain brightness, what we can do is we can add another bulb, like say we add it here, and it seems pretty obvious that the brightness of both bulbs will decrease, and if they're the same, then they'll be half as bright as they were initially, and that's because each electron that flows out of the cell has to flow through both of them and has to share its energy across both bulbs, so you find that they are dim. And it doesn't matter how many bulbs you add, you're going to keep decreasing the brightness, and I hope it makes sense to you that the cell will run out of charge just as fast as if there were 5 bulbs as if there is one, because it's either giving all of its charge to the one bulb or it's sharing it out equally between the 5, but either way it's giving out the same amount of charge, so it will run out just as quickly. So series circuits are pretty crap, to be honest. Maybe I shouldn't have said that. Oh well. Now I'm going to draw a parallel circuit, and I'm going to do a similar setup with 2 bulbs, but just like this. Okay, in this case, what will happen is the bulbs will be just as bright as they were before, and the reason is because each electron that gets pushed around the circuit, it has to have a path to, it has to choose a path to go through. So it'll either go through the first branch or go through the second branch, but it can't go through both at the same time. So that means the output of the cell needs to be twice as much now that there are two bulbs in parallel. So what you find is the brightness of the bulbs are the same, and therefore the cell will run out twice as quickly, and that's because more electrons need booting out per second. And there are a couple of circuit rules you need to know, which is things like this. So in a series circuit, the current is the same everywhere, and then the voltage of the individual components adds up to what is coming out of the cell. Whereas in a parallel circuit, why am I trying to delete this in the middle of discussing it? It's so annoying. You find that the voltage is the same everywhere, and the current adds up. And if this isn't making a huge amount of sense, I'll show you some examples soon when I get on to the mathematical part of electricity. But that's just worth bearing in mind. So let's move on to another slide. And we're just going to quickly talk about Ohm's law. So Ohm's law states that the current through a resistor at a constant temperature is directly proportional to the potential difference across the resistor, and that means basically that if you draw a graph of current, remember current is given by I and potential difference, you find that in a resistor you have a straight line, because directly proportional means a straight line. If I had a ruler, that would be straighter. So yeah, because as the current increases, yeah, the voltage will increase. However, some components don't obey Ohm's law, and the key examples here, and I really would only learn this much, is the filament bulb, which has a very characteristic S-shaped curve, and the diode, which looks like this. Just be able to recognize these things. And what that tells you from the filament bulb's point of view is what I was trying to explain earlier, which is that as the resistance of the metal filament increases, as its temperature increases, and this is because the ions in the metal filament vibrate more as the temperature increases, so they resist the passage of the electrons through the filament more. The diode has this distinctive shape because in the forward direction you find that the current is not directly proportional to the potential difference because it is not an ohmic conductor, and in the reverse direction the current is negligible, so the resistance is much higher. And if you don't like what I just said, literally just know that that is a diode right here, because that's how they always draw them. I think I'm getting near the end of what I wanted to talk about. I just wanted to say that resistance has the unit of ohms, and in a series circuit the resistance of the individual components adds up to the total resistance of the circuit. And I think now it's time to do a couple of calculations using some formula triangles so that you're happy with what's going on there. Question 7. A student set up an electrical circuit shown in figure 9. Okay, the ammeter displays a reading of 0.1 amps. Calculate the potential difference across the 45 ohmic resistor. Right, let's not get confused. So this thing here is the battery. This is the ammeter, which measures current. This is a regular resistor, another regular resistor, another regular resistor. This is an open switch. I'm going to have to use lots of equations here. Because we've got current and we've got resistance, so we've got R and we've got I, we're looking for potential difference, which is otherwise known as voltage. Which formula triangle involves those variables? It's VIR. So we need the equation V equals I times R, which equals 0.1 amps, times it by 45 ohms, to get an answer which is 4.5 volts. Part 2, calculate the resistance or the resistor labelled R. And now this is more difficult. This requires you to understand circuit rules. So let's first of all work out a few things. First of all, because it's a series circuit, remember that the voltage is shared everywhere. So there's 12 volts there, but that means the individual voltages must add up to 12 volts. So we've just found out that the voltage here is 4.5 volts. The other thing to notice is because the ammeter is displaying a reading of 0.1 amps, Remember, because it's a series circuit, we're going to have the same current absolutely everywhere. So we know that it's going to be 0.1 amps here, 0.1 amps here, 0.1 amps here. So first of all, we're going to work out this voltage here, because it will help us work out our final answer. So we're going to use the equation V equals IR to do that. So 60 times 0.1, which gives us an answer, which is, I am so bad at doing these sorts of calculations in my head. I always screw them up, so I'm going to look stupid and do it now on my calculator. Yeah, so that is 6 volts. And therefore we know, because I just told you, that individually that and that must add up to 12 volts. We need to work out the voltage here. So we simply do 12, take 6, take 4.5 to get 1.5. So we know that this voltage along our resistor is 1.5 volts. So now in terms of working out the resistance, so VIR again, resistance equals V over I. So we know V is 1.5 divided by 0.1 amps to give us a resistance which is 15 ohms. It is worth 3 marks. It's quite a long, hard question. State what happens to the total resistance of the circuit and the current through the circuit when the switch S is closed. So what will happen is, if you have a look, there's an alternative route, which means it's not going through the 60 ohm resistor anymore, which means the total resistance decreases, meaning that the current increases. A student investigated how current varies with potential difference for 2 different lamps. Her results are shown in figure 10. Complete the circuit diagram for a circuit the student could have used to obtain the results shown in figure 10. Well, they haven't even listed the components. Okay, so we definitely need some lamps including. We need a way of measuring the current, so we're going to include an ammeter. Remember, an ammeter must always be added in series. We need a voltmeter because it says on the x-axis potential difference in volts, so that needs to go in, and remember, because it's a voltmeter, it has to go in parallel. I'll actually show you what that looks like. So we need a ammeter connected in series. Here's our lamp. As I said, we needed the voltmeter added in parallel, which is why it comes off as a separate branch. And because we're altering those, we do need a variable resistor, which looks like a box with a funky arrow going through it like that. So that's your answer. 8 part 2, which lamp will be brighter at any potential difference? Explain your answer. Use figure 10 to aid your explanation. Okay, let's have a look at the graphs then. So we know that A will be brighter because it has a higher current compared with B at any potential difference. And as a result, it has a higher power output. Because remember PIV, which is power equals current times voltage. So if current is higher, then power will be higher. You know what? These papers are hard. They're expecting you to be able to juggle a lot of stuff. Lamp B has a high resistance at any potential difference. Explain how figure 10 shows this. So again, if we look at the graph, we can see that there's a lower current than lamp A for the same potential difference, and we can see from the slope of the line that it has a lower gradient. So B has a lower gradient compared with A. Both lamps behave like ohmic conductors through a range of values of potential difference. Use figure 10 to determine the range of these lamps. Explain your answer. Whoa, that's hard again. So first of all, you need to state or know Ohm's law, which is that the current through a conductor between 2 points is directly proportional to the voltage against 2 points. So you're looking for the portion of the graph where the line is straightest, which is actually near its origin. So you're looking around these bits here. And so what you then have to do, I need to turn back to the question. What you then have to do is determine the range of values of potential difference which enable you to say the lamps are obeying Ohm's law. So have a look again at that graph and you'll see that it's between 0 and 2 volts. And that's why, and it's just here, it's straight here, straight here. So they think the range, remember range is the difference between the highest and lowest values, is 0 to 2 volts. That's so hard. And then effectively you're stating Ohm's law, which is that, as I said, for an ohmic conductor, current is directly proportional to potential difference, and the third available point states that the resistance will therefore be constant. So it is worth learning Ohm's law. 13. An electrician is replacing an old electric shower with a new one. The inside of the old shower is shown in figure 19. If the electrician touches the live wire, he'll receive an electric shock. Explain why. So this is worth learning this answer off by heart, and this is because the potential or the voltage of the live wire is 230 volts, whereas obviously the electrician isn't charged, so his potential will be 0 volts, meaning that there's a large difference between the live wire and electrician's potential, causing that charge or current to jump to his body. Different electrical wires need to have a cross-sectional area that is suitable for the power output. Figure 20 shows the recommended maximum power input to wires of different cross-sectional areas. The new electric shower has a power input of 13.8 kilowatts. Determine the minimum diameter of wire that should be used in the new shower. The diameter D can be calculated using this equation where A is the cross-sectional area of the wire. Don't get too panicked. It's just a matter of substituting these numbers in. So we're looking for a power input of 13.8. So you're going to put a line across from 13.8 to here. Bring that down. So inaccurate. I think the cross-sectional area therefore is 9.5. We're looking for D, so we're just going to write D equals 4 times that number we've pulled off the my phone's driving me mad. So 4 times 9.5, which we pulled off the graph, divided by pi, and then when you pop that into your calculator, you should get, where is my calculator? So yeah, I popped that into my calculator and I got a value which is 3.5, which fits in the area, which fits in the answers that they're allowing, so that's good. The charge that flows to the new shower in 300 seconds is 18,000 coulombs. The new electric shower has a power of 13.8 kilowatts. Calculate the resistance of the heating element in the new shower. Write down any equations you use, so that's worth 5 marks. So we're going to have to do quite a lot of maths here. Now, what do we need to find out? We need to find resistance, which is R. We've been given T, which is time, a charge, which we know is Q, and we've been given a power rating, which is P. So we need to work out a combination of equations that will help us get to R, and this is what you're going to use. You're going to use charge is current times time as an equation. You're going to use voltage equals current times resistance to help you find R, and the last one you're going to use is power equals current times voltage. So the way you're going to do this, because this is fundamentally the equation we're trying to get to, the one which will enable us to calculate resistance, because that's what they've asked us to find. But unfortunately for us, we don't have either a V or an I, so we're going to use these other equations to find those values. So starting with Q equals IT to help us find current, substituting the values we've been given. So the charge is 18,000 equals I, which we're after, times T, which we were told is 300. So do 18,000 divided by 300 to get 60 amps as our answer for the current. Then we're going to use power equals current times voltage, and I'm using all the equations, I'm writing them out because it's good practice, and also they've asked us to do it in the question. So we've been told power is 13.8 kilowatts, so you need to convert that to just watts by timesing it by 1,000, so it becomes 13,800 equals I, which we just worked out is 60 times V. To get V by itself, divide both sides by 60 to get a voltage of 230 volts. And now we're ready to work out resistance. So resistance is V over I. We've just worked out V, which is 230. Divide it by 60, because that's the amps, which gives us a resistance value of 3.83. Done.
So let's first of all look at density. Now density is all to do with how heavy an object is relative to its volume. So something like a block of concrete, if you get the same size block of wood, obviously the concrete is going to feel much heavier, and that's because it's far more dense. If you look at the definition of the density of a substance, well, it's mass per unit volume. So the equation for calculating density is therefore density equals mass divided by volume. Use the physics triangle, drunk men vomit, with D at the bottom, M at the top, V at the side, and that will help you rearrange that equation 3 times. So like I said, it's all about how heavy a substance is relative to its volume. Now, sometimes they ask you to calculate the density of an object.
Now, if you have a perfect cube, it's quite easy to do that. First of all, you measure the volume of the cube. So obviously you get something like a meter ruler or a millimeter ruler, totally depends on the size of the object. You're going to calculate the three sides, so its height, its width, its length, and then you're going to multiply those together to work out its volume. Now, you might need to use calipers depending on the object, but just be prepared to state a piece of equipment that you can accurately calculate the volume of an object with. Then you're going to calculate its mass, so you just need to put it on a top pan balance and weighing scales, get its mass either in grams or kilograms, and then substitute both of those numbers into the equation density equals mass divided by volume, and before you know it, you've got the density of the object. Now, if you've got something like a pebble that's more irregular, that's going to be more difficult to measure the volume of. So the easiest way to do that is to place it into a measuring cylinder of water. So for example, if you start with a measuring cylinder that contains 100 centimeters cubed of water, you add the pebble and it goes up to 120 centimeters cubed, you know therefore that the volume of the pebble is 20 centimeters cubed. Now, to work out its mass, again, you're going to pop it on a top pan balance, so that's not too difficult. If you're asked to calculate the density of a liquid, then you're going to work out its volume again using the measuring cylinder. That's going to be nice and straightforward, and then you're going to measure the mass of the measuring cylinder without any liquid in it, with the liquid in it, and the difference between those two numbers will be the mass of liquid. So that's just some kind of experimental stuff to do with measuring density. Now we need to look at states of matter. So remember the three states you need to know about are solid, liquid and gas. So if you do a change in state, then you're going between a gas to a liquid or a liquid to a solid, that sort of thing. And if they ask you what sort of change that is, it's a physical change, and that's because no other product is made, so theoretically you could easily switch between the different states. Let's look at the change in state triangle. So obviously if you go from a solid to a liquid, then you are melting. If you go from a liquid to a solid, then you are freezing. From a liquid to a gas, it's either boiling or vaporizing. And then from a gas to a liquid, that is condensation. So that's what happens in the shower when it gets all steamy and it hits the window and it turns back to a liquid. Sublimation is a weird one. That's when a solid turns directly into a gas, and an example of that is something like carbon dioxide with dry ice, or solid iodine, but that's more of a chemistry question. We say that changes in state involve a conservation of mass, and all that means is the mass doesn't change when an object or substance changes state, and that's because the number of particles remains unchanged. So if you have a block of ice and then you turn it into a liquid by melting, then you've got the same number of water particles, so therefore the mass should stay the same. Then the next bit's just a bit boring, but it's all about stating the difference between solids, liquids and gases. You need to talk about the particles' movements, you need to talk about the forces holding together the particles, whether they can flow, their density, and be able to draw diagrams. So remember, in a solid, all the particles are packed nice and closely together. You need to draw a really uniform shape here, so be careful when you're drawing those particles. You're going to say that they vibrate around in fixed positions. You're going to say that they don't flow, that there are strong forces holding together the particles, so they occupy a fixed volume, and they have in general a high density. Now a liquid, you're going to say that it does flow, you're going to say that it fits into the container shape, and you find it at the bottom, so don't fill up the whole block with a liquid, because clearly if you drunk some of your Coke, you have a gap at the top. It's not like the Coke fills the whole bottle. You've got intermediate size forces between the particles. You've got a slightly lower density than a solid, a higher density than a gas. Particles move randomly, and that is why the liquid can flow. With a gas, the forces holding together the gas particles are very weak, so the gas flows very easily to fill the entire volume of the container in which it's found. Weak forces holding together the particles, no fixed shape. More definitions now. Clearly the melting point of a substance is the temperature at which a substance melts, the boiling point, the temperature at which it boils, etc. Now the key thing to remember here is that if you have a pure substance, and that's a substance with no other impurities at all, what happens is that when it changes state, its temperature stays the same the entire time while it is changing state. So it's not like the first few molecules start boiling and therefore the temperature changes. No, while the whole substance is taking its time to boil, the temperature will be the same. So in the case of water, that'll be 100 degrees Celsius. And that's why you get the very characteristic graph when you're looking at the melting and boiling of water, for example. So it'll go up and then it will level out. That's while the water is melting, then it'll go up again, and then you get a very straight line again for quite a long time, and that's when the water is boiling. Another definition is latent heat, and that's the energy transferred to a substance whilst it changes state. Now we get even more dull and we start talking about internal energy, and this is the energy stored by particles in a substance. And it's made up of the total of two things. It's the total of the kinetic energy of the particles and the potential energy of the particles, which is due to the relative positions they are found from each other. You may be asked to use the specific heat equation, and that's all to do with calculating the energy of the substance. It's fairly straightforward. The equation here though is E, so that's change in energy, equals mass times specific heat capacity times temperature change. So they could give you an experiment where they're heating some water. So the way you'd calculate the energy change of the water is you'd get the mass of the water, for example 100 grams, you times it by its specific heat capacity, which is actually just a very specific number, and then times it by the temperature change given in the question, and then you substitute all those numbers in and you'll get an energy change, which therefore will be given in joules. I'm trying to think of exam type questions they may ask you. They may ask you about how puddles evaporate on a hot day, or how water boils, and you're just going to say that the particles gain kinetic energy, and those particles which gain the most kinetic energy will escape first, and they'll escape from the surface of the liquid, and because they've escaped, it means that the remaining particles have lower average kinetic energy, and that's the sort of answer you need to rote learn, and I've seen it come up lots of times in various examples, so I think it's sensible learning that. Another terrible definition is the definition for the specific latent heat of fusion, and that's the energy needed to change 1 kilogram of a substance from a solid to a liquid. The specific latent heat of fusion is given by the equation energy divided by mass. Now the specific latent heat of vaporization is the amount of energy required to change 1 kilogram of a liquid to a gas, and the equation for calculating that is very similar to the one I've just mentioned. The point is, when you're calculating pressure, you need to know about both force and area. To have a high pressure, you're going to need a force which is applied over a small area, and to have a low pressure, you're going to need a force which is applied over a large area. So if we look at our formula triangle, we see that it contains force, area and pressure. Force goes at the top, then it goes area, then it goes pressure. It's worth learning this triangle. We have many things in everyday life which will be designed in order to either increase pressure or decrease pressure depending on their use. Something like a knife or a drawing pin, for example, they need to be sharp. So what you need to do is apply a force over a very small area to increase the pressure. And that's to make knives really sharp so you can slice through things, and it's to help you stick a drawing pin in the wall. You'll notice that the drawing pin has a nice wide top, and that increases the area, therefore decreasing the pressure, and that means that the pin doesn't actually stick itself into your thumb, because that wouldn't be very helpful, of course. There are other applications of pressure which you need to know about, and that will be applications which aimed at decreasing pressure. So things like elephants' feet and camels' feet, they don't want to be sinking into the sand, so they need to be applying a much lower pressure. The way they do that is by having really large feet, because what these do is they spread the force, so the weight of the animal, over a really large area to help decrease pressure, and that will help stop the animal from sinking into the sand.
Here I'm looking at a question, so which exerts more pressure on the ground? A tank with a weight of 80,000 newtons or a cyclist with a weight of 1,000 newton? The tank tracks have a contact area of 10 metres squared, and each of the cyclist tyres have a contact area of 0.6 metres squared. So what you need to do is begin by drawing the triangle to help you sort out your formula. So it looks like this: force is at the top, then it goes area, and then it goes pressure. So I'm going to change to black. So I'm obviously looking at the pressure, so I need the form of the equation which looks like this: force over area. I'm going to start by looking at the tank. So its pressure will be its force, and obviously that will be the 80,000 newtons. Why? Because weight and force have the same units, so that is newtons, and therefore we can use them interchangeably. So that's 80,000 divided by the area, which I've been told is 10. And here's the answer, 8,000 newtons per metre squared. Now let's look at the cyclist. Okay, so the pressure will equal the force again, which is this time 1,000 newtons, divided by the area. Now don't make a mistake here. the area is 2 lots of 0.006. The reason being because obviously the cyclist has 2 tyres. So I'm going to do 0.06 times 2, which equals 1,000. Please don't let me run out of space. By 0.012. I'm going to use the calculator here. And the answer here is 833 newtons meters squared. So, as you can see, it's obvious that the cyclist exerts more pressure because their pressure is 83,333. So make sure you write that the cyclist is the answer.
Question 4. A diver works in the sea on a day when the atmospheric pressure is 101 kilopascals and the density of the seawater is 1028 kg per m cubed. The diver uses compressed air to breathe underwater. 1,700 litres of air from the atmosphere is compressed into a 12-litre gas cylinder. The compressed air quickly cools to its original temperature. Calculate the pressure of the air in the cylinder. The only reason these questions are hard is because you need to actually pull out the information in the question, but once you've done that, it's straightforward enough. So what numbers have we been given? Well, we've been given atmospheric pressure of 101 kPa, density, which is here, but I don't think we need to use that quite yet. We've been told that 1,700 litres of air is compressed into a 12-litre gas cylinder. So we can see here straight away we've got 2 volumes, we've got a pressure, and we've got another pressure. So which equation contains 2 lots of volumes and 2 lots of pressures? Well, it's this one. Correct me if I'm wrong, but I think this is given on the front of your paper, but it's quite straightforward to remember anyway. Just make sure your units are all the same and then start subbing in these numbers. So pressure 1 is going to be 101 times volume 1, which is 1,700, equals, we're looking for P2, so we'll keep that there, times 12. And then the way to work this out is work out the left-hand side first of all. So 101 times 1,700. And then divide both sides by 12. And then when you round that to 3 sig fig, you're going to get P2 equals 14300. The units will be kilopascals. State the equation linking pressure difference, depth, density, and G. So you can write this out in words. You can literally write pressure difference equals depth times density times G. Or you can write it out as symbols, which would be P equals H times, remember it's the Greek letter rho, which looks like a P, so that's why it's a bit confusing, times G. So if in doubt, I would write it out in words. Whatever you do, don't write gravity for G. They're very fussy over this. You need to write acceleration due to gravity. Calculate the increase in pressure when the diver descends from the surface to a depth of 11 meters. So what you're going to do here, I'm just going to write out the equation. So pressure equals height times density rho times G. So 11 times density, which we were given right at the beginning of the question, which is 1028 times G, which is 10, and we need to know that number. You can use 9.8 also, but 10 is easy. And then you work that out and you get an answer which is 110 kPa. Part 3, calculate the total pressure on the diver at a depth of 11 meters. Assume that the atmospheric pressure remains 101 kPa. Well, because it's worth only 1 mark, they've only given you a small gap. You shouldn't be doing any proper calculations here, so no substituting into equations. You simply need to add together your previous value to the atmospheric pressure. So that's 101 plus 110, which equals 211 kilopascals. C. As the diver breathes out, bubbles of gas are released and rise to the surface. The bubbles increase in volume as they rise. Explain this increase in volume, 2 marks. Make 2 separate points. One of the most basic arguments you can make here is that it will be warmer closer to the surface of the sea because you're closer to the sun. That would be worth 1 mark. And what that does, because remember, if it's warmer, the particles vibrate more, and therefore the pressure will increase inside the bubble, which leads to its volume increasing. Or you could give an argument to do with the fact that pressure decreases closer to the surface. Always provide an equation in this case, so that would be pressure equals height times density times G. And then you would state that the PV value is constant for a fixed mass of gas. And if that sounds weird, you can state the other pressure equation once again, which is P1 times V1 equals P2 times V2. The diagram shows some gas particles in a container. The piston can be moved in or out to change the volume of the gas. Add arrows to the diagram to show the random motion of the gas particles. Just literally show them just moving around really randomly. Just make sure you add enough arrows. They're just a gas, so it's quite straightforward. Explain how the motion of the gas particles produces the pressure inside the container. This is an answer you can rote learn. So you want to first of all talk about the fact that gas particles have random motion and that they collide with the walls of the container. Then this creates a force, and then lastly state an equation which is pressure equals force over area. And that is the easiest way in which you'll get 3 marks. I would really recommend you learn that answer off by heart. State what would happen to the pressure if you push the piston into the container without changing the temperature. Well, you've got a smaller volume, so therefore the pressure would increase. When the gas in the container is heated, the piston moves outwards. Place ticks against the 3 correct statements. The gas particles get bigger. No, that's not true. The mass of gas particles stays the same. Yeah, that makes sense. The gas particles move faster. Well, clearly, if you heat them, they're going to gain kinetic energy, so they will move faster. The average distance between the gas particles increases. Again, true, because if they're moving faster, they'll be moving away from each other, therefore increasing the distance. The temperature of the gas decreases. Well, no, the container's been heated, so that's actually absolute rubbish. Did you chase a lot of birds?
It's really important when you begin this topic that you understand a lot about the nucleus. So remember, the nucleus of an atom contains the neutrons and the protons. The protons have a mass of 1, neutrons have a mass of 1, and then the other atomic particles you need to know about are the electrons, and they obviously exist in the shells surrounding the nucleus, and they have a very tiny mass. The number is actually 1 divided by 1,840, but it's very, very small. So remember, the mass number of an atom is found by adding together the protons and the neutrons. It's also important that you know the definition of the word isotope. Isotopes are atoms of the same element with the same number of protons but different number of neutrons. So that means you have, for example, carbon-12, carbon-14. They are both carbon because they have an atomic number of 6. I hope it's 6, I think it is, if I remember rightly. But they have different mass numbers. One has a mass number of 12, the other one has a mass number of 14, which tells you that it has 2 extra neutrons. I think we can get straight into it now. Remember that the reason why an atom is radioactive is because there are too many neutrons in the nucleus, which renders it unstable, and it's likely that this unstable nucleus will emit radiation in order to help it become stable, and it will emit different types of radiation. It will either be alpha, beta or gamma. Starting with alpha radiation, what you find is that when a nucleus emits alpha radiation, it emits a helium nucleus. That's to say that it emits 2 neutrons and 2 protons. That therefore means that when you're writing the radioactivity equations, what you need to do is you need to take 4 off of the mass number to find your element's new mass number, and you need to take 2 off the atomic number, because remember, the atomic number and the proton number are the same. And I'm actually going to insert some examples here.
You'll be given the name of the element or the symbol and its mass number and atomic number, and you're going to have to work out how that changes when it emits a alpha particle. I just told you that an alpha particle is made up of 2 protons and 2 neutrons. Each proton has a mass of 1, each neutron has a mass of 1. So if you lose 2 protons and 2 neutrons, you find that the mass number will go down by 4. And remember, the mass number is the top number here. And then the proton number, because 2 have been lost, remember the proton number is the same as the atomic number, so the atomic number, which is the bottom number, will have gone down by 2. So that's 88, and this element will now be a new element because obviously the atomic number's changed, and it's radon. And then you complete it by writing the alpha mass and proton number there. And remember, alpha is a helium nucleus.
Next up is if you have beta radiation. Now this time a neutron turns into a proton and emits an electron, which is actually the beta particle. So when we're looking at the equation, what you find is the mass number actually stays the same. Why is that? Well, at the beginning I told you that the protons and the neutrons both have a mass of 1. So if a neutron turns into a proton, the mass stays the same. However, because you've now gained an extra proton, you will find that the atomic number, the proton number of the element, will have increased by 1. So that's what you need to do in a beta decay equation.
Now I'm going to talk you through beta decay, and we have potassium here. So potassium has a mass number of 40, it has an atomic or a proton number of 19. Remember, in beta decay, the neutron turns into a proton, so what you'll find is that the mass number will stay the same because they both have the same mass. However, because a proton has been gained, it means that the atomic number will go up by 1. So you find that the mass stays at 40, the atomic number goes up by 1 to become 20. Because we have a new atomic number, we have a new element, and it will actually be calcium. And then I'm just going to finish off by writing the beta particle here.
Okay, lastly, gamma radiation. Gamma is very different from alpha and beta decay. It is a wave, it's a member of the electromagnetic spectrum. Check out my video on that if you're less certain of that topic. But remember, it's a very high frequency wave, full of energy, and therefore when you emit gamma radiation, neither the mass number or the proton number will change. Okay, you need to know now about the varying penetrating powers and ionizing powers of those 3 types of radiation. First of all, remember what an ion is. An ion is a charged particle. It's an atom which has either lost or gained electrons. So the more ionizing the radiation, the more likely it is to cause an atom to gain or lose electrons. Alpha radiation is the most ionizing, beta is moderately ionizing, gamma is not very ionizing at all. Okay, it's weakly ionizing. That means the type of radiation you least want to enter your body is alpha, because what it will do is it will cause lots of issues, because it will cause mutations to happen to your cells which could lead to cancer and a tumour developing. In terms of penetrating power, what we mean by that is how far the type of radiation travels before it is stopped. Now, alpha will only travel a few centimetres in air before it's stopped, which is why it's not very dangerous to have an alpha source near you, because actually it's never actually going to reach you to cause you to have a mutation, to cause you to have cancer. So alpha radiation isn't dangerous outside the body, but it's very dangerous inside the body because it's very ionizing. Beta, like before, when we were talking about its ionizing powers, this time it's moderately penetrating, so the way we stop that is using aluminium. Gamma is very penetrating and can actually only be stopped by several centimetres thick of lead sheeting or a meter's thickness of concrete. So gamma is very dangerous outside the body because it finds it very easy to reach us and therefore cause mutations. So you definitely don't want to come into too much contact with a gamma radiating source. Oh, this video is going very well, I'm happy. So lastly, I need to talk about the various uses of these various types of radiation. There's quite a few uses, things like smoke alarms, tracers, carbon dating, checking to see if there's leaks. So I'm going to take each one in turn and try and give you a whistle-stop tour of all the uses. Let's start with the smoke alarm. Okay, what happens here is in your smoke alarm you have a small alpha source, so it's emitting alpha radiation. What happens is the alpha radiation meets air particles, and what that does is it creates a small electric current which is picked up by a detector in the smoke alarm. So when everything's nice, there's no smoke, there's no fire, you'll find that this current is reaching the detector, so the detector's happy, so it's not going off. However, when there's a fire, there's lots of smoke and soot in the air, so actually what happens is it blocks the alpha particles, and we know that they don't travel very far, so the smoke particles get in the way of the alpha radiation, therefore no ionization of air particles can happen, so there's no electric current. So the detector is like, hey, there's no current, and therefore it knows that there's a fire, hence the alarm will sound. So it's actually really clever. The second use I'm going to talk about is making paper and aluminium foil the right thickness. This time we're talking about beta radiation, and all that happens is you have a couple of rollers which roll the aluminium or paper out to the right thickness, and then there's a detector and a beta source. So the beta source is sending through beta particles. Next up, we're going to talk about tracers. Now, these are special chemicals we add to our bodies to work out if there's anything wrong with them. So a doctor might think there's something wrong with your kidneys. So what they do is they'll give you a dose of iodine. And what that does is it travels around the body. When it gets to the kidney, it will pass through it or it won't pass through. And the doctor can get a scan to show whether it's passed through or if there's a blockage. So it's a really good way of identifying if there's any problems with various parts of your body. Now, the reason why they use iodine is because it has a short half-life. Remember, I'm going to film a video on half-lives, but that's a good thing because it only has a half-life of 7 days, which is good because you don't want all of this radioactive iodine staying in your body, potentially causing you harm. However, 7 days is long enough for you to actually have a scan so it's the perfect length of time. Second point is that it produces a stable isotope, which again is really important because the last thing you want is an unstable isotope in your body emitting radiation. They use gamma radiation for detecting leaks in water pipes. What they do is they add a gamma source to the water, it flows through the pipes under the ground. There's a detector above the ground which is detecting how much gamma radiation there is in the water. If it suddenly detects a lot of radiation, it tells you that there's a leak above the pipe, because it means that the water is escaping up into the ground and therefore a far larger reading is received. Lastly, I think I just want to talk about carbon dating. So we use carbon dating to determine how old a sample of plant material is. Remember, plants use carbon to grow. They use it in photosynthesis in the form of carbon dioxide. Now, some of the carbon they'll take in will be radioactive, and obviously that will decay over time. However, when they die, they can't take in any more carbon because they're dead. So if you compare the amount of carbon that they have now compared with when they were alive, you can definitely see how old they are.
The radioactive isotope sodium-25 has a half-life of 1 minute. What fraction of it remains after 3 minutes? So what you have to do here is work out how many half-lives have occurred. And because it's 3 minutes and 1 goes into 3 minutes 3 times, 3 half-lives have occurred. And then all you have to do, because you're finding out a fraction, is do a half times a half times a half to find that 1/8 remains after 3 minutes. Question 3. Xenon-133 is a radioactive gas used for diagnosing lung problems. In 15 days, its activity falls to 1/8 of its original value. What is its half-life? So we need to work out how many half-lives occur to get to 1/8. So what you need to do is, you might have to do trial and error, but you need to just do as many half-lives as you need to in order to get to 1/8, and the answer is actually going to be 3 of them. So 3 half-lives occurred in 15 days. So how long did it take for 1 half-life to occur? Well, you just need to do 15 divided by 3, and the answer is 5. So 5 days is its half-life. Question 4. The half-life of the radioactive isotope sodium-24 is 15 hours. A sample has a count rate of 240 counts per minute. Its count rate 60 hours later will be... Okay, so this time again we need to find out how many half-lives have occurred. So I'm going to do 60 hours divided by 15, and I see that 4 half-lives have occurred. So therefore, after 1 half-life, 120 counts would remain, but there were 4 of them, so I'm going to times it by a half 4 times, and that is the same as 240 times answer, and that is 15 as my answer. So its count rate after 4 half-lives have occurred, so I've divided 240 by 2, or times them by half 4 times, and I have got 15 as my answer, so that's 15 counts per minute. Question 5. A radioactive isotope of silver has a half-life of 20 minutes. A sample gives a rate of 6,400 counts per second at 9 o'clock. At what time will the count rate be? About 200 counts per second. Okay, this sounds hard, but again, just use trial and error to work out how many half-lives have occurred. So I'm just going to do 6,400 times a half, and I've got 3,200, so I'm going to times it by half again, and I'm going to keep going until I get to 200. And actually what I found here is that it has taken 5 half-lives in order to get to 200 counts. So all I did was times 6,400 by a half 5 times, and I got to 200. So like I said, that means 5 half-lives have occurred, and each half-life took 20 minutes, so therefore 5 half-lives takes 100 minutes. So all you need to do now is work out what 100 minutes past 9 o'clock is, and remember there's 60 minutes an hour, so that brings us up to 10:40. That one was quite hard, but you can work it out. Like I said, just use trial and error to work out how many half-lives have occurred. Practice doing as many questions of these as possible in order to get good at answering the different types of question. Remember, when you're reading off graphs, to look at, you can read off the half-life by looking at how long it took for the counts to reduce by half, and then you need to read across to see how long that took. Take into account background radiation, because you'll see that the
graph line will never actually touch the x-axis, and that's because background radiation exists, and remember that that comes from things like cosmic rays, x-rays, rocks, just general stuff really. And remember, half-life is actually the amount of time taken for half the radioactive nuclei to decay.
Now, how is it carried out? What they do is they fire a neutron at something like uranium-235, so that's your atomic nuclei, and what happens is that nuclei splits and it sends off 2 or 3 other neutrons which go off and hit other uranium nuclei which split, and before you know it, a chain reaction is set up, and we can see very quickly that that could become out of control. Now, why do we even bother doing this? It's because we're really interested in the huge amount of energy that this generates, and if they ask you about the type of energy generated, you need to say that it is kinetic energy. And we're interested in generating this huge amount of energy because we can then harness it to produce electricity. So if they ask you how nuclear fission can lead to the production of electricity, you simply need to say that the energy released is used to heat water, and that water is used to generate steam. Then point out that steam turns a turbine, and lastly say that the turbine turns a generator, and that is indeed what produces electricity. So it's a very useful reaction. However, there are massive advantages of nuclear power in the fact, I'm going to touch on this now, the fact that it generates a huge amount of energy. However, and it's a very reliable source of energy. However, there are disadvantages. First of all, it's unrenewable, because once that uranium nuclei runs out, you can't generate anymore. Secondly, you've got problems in case any of that radioactive waste that's produced, you need to store it really carefully, because if it's allowed to escape into water sources underground, before you know it, you've got a contaminated water source, and if there's radiation in the water, then that can lead to mutation of cells, which leads to cancer, so lots of issues there. And the third disadvantage is the high decommissioning costs. What that actually means is, I think nuclear power stations can only run for about 20 years, I don't know why, but effectively at that point they then need to be taken apart, and clearly because of all the radiation, that's going to be a very expensive process. Anyway, I don't really want to talk too much about that. I want to go back to the crux of nuclear fission. I want to talk about what's happening inside the nuclear reactor. So as I said previously, we have a massive chain reaction that's setting off, and we need to control that, because otherwise a massive explosion could occur and it could kill lots of people. So the nuclear reactor is very specifically designed to prevent it becoming out of control. It has things called control rods. What they do is they dip down into that uranium, and what they do is they absorb excess neutrons. So rather than 2 to 3 neutrons getting released and hitting more nuclei, which release another 2 to 3 neutrons, and a huge amount of energy is released, they absorb excess neutrons, allowing only 1 neutron to be fired off each time, and that will obviously slow down the entire reaction and keep it safe. You've got a moderator, and that slows down the neutrons, and again that will control the speed of the reaction. And you have a coolant, again that will absorb some of the kinetic energy of those neutrons, again slowing down the reaction. Surrounding the nuclear reactor you'll find a shield or shielding, and that tends to be made out of steel or concrete. One question they like to say is, so why does the shielding exist? So you want to say to prevent that radiation escaping, and you need to point out that that radiation is very penetrating for a second mark, which means it but it can travel a long way through the air, so that's why that shielding is there to stop it.
9. A student models the random nature of radioactive decay using 100 dice. He rolls the dice and removes any that land with the number 6 facing upwards. He rolls the remaining dice again. The student repeats this process a number of times, and table 1 shows his results. So obviously when he didn't roll, he had 100 dice remaining. Then he rolled once and he had 84 dice remaining, so that means that 16 of those original 100 dice landed on 6, and he continues. Give 2 reasons why this is a good model for the random nature of radioactive decay. The reason being because radioactive decay is really random, and so you never know which atom will decay and when it will decay. So the reason why the dice is good is because you can't predict which dice will decay, and you can't predict when the dice will decay. The students' results are shown in figure 11. Use figure 11 to determine the half-life for these dice using this model. Show on figure 11 how you work out your answer. Okay, so half-life is all to do with making sure you've got half the number of dice remaining, so that's at 50. You've got to show it, which means you need to draw some nice straight lines on your graph and then read down on the x-axis. that would have been slightly shifted along, so that would therefore be 3.6. A teacher uses protactinium PA generator to produce a sample of radioactive material that has a half-life of 70 seconds. In the first stage in the protactinium generator, uranium decays into thorium and alpha radiation is emitted. The decay can be represented by this equation. Determine the atomic number of thorium 234. So remember, with alpha radiation, what's happening is that 2 protons and 2 neutrons are being given off. That means that the mass number decreases by 4, and as we can see, it's gone down to 234 from 238. In terms of what happens to the atomic number, that's the same number as the proton number. So if you lose 2 protons, clearly the new number here will be 90. When protactinium decays, a new element is formed and radiation is emitted. The decay can be represented by the equation shown in figure 13. When protactinium decays, a new element X is formed. Use information from figure 12 and 13 to determine the name of the element. Just remember, the element is dictated by its atomic number, its proton number. So you're looking for an element that has a proton number of 92. And if you look back up here, you can see in figure 12, uranium has a proton number of 92, which is why the element is uranium. Determine the type of radiation emitted as protactinium decays into a new element. Give a reason for your answer. So we're having a look again at these numbers. So it's very important that you have a look here. Now, in beta radiation, what happens is a neutron turns into a proton. Because they both have a mass of 1, despite the fact you've lost a neutron, you've gained a proton, so there's no net change in mass number, so 234. But because you've gained a proton number, it goes up to 92, which is why you know that this is beta radiation. So you're literally going to write it's beta, and that's because the proton number has gone up by 1. 9.6. The teacher wears polythene gloves as a safety precaution when handling radioactive materials. The polythene gloves do not stop the teacher's hands from being irradiated. That's true. You need stuff like lead and aluminium depending on the type of radiation. Polythene would do nothing. Anyway, explain why the teacher wears polythene gloves, and mainly that's to prevent contamination to the radioactive material. 10. Electricity is generated in a nuclear power station. Fission is the process by which energy is released in the nuclear reactor. Figure 14 shows the first part of the nuclear fission reaction. Complete figure 14 to show how the fission process starts the chain reaction. Make sure you include enough detail here. So remember, when that neutron hits the nucleus splits into 2 daughter nuclei. So I'll probably label those just to be on the safe side. So that's a daughter nuclei. And it releases 3 neutrons each. So we're drawing those nice and small because we need them to resemble the original neutron. I might label them neutron, and then they go off and hit a daughter nucleus. Another uranium nuclei. So that's why we have to draw the big balls. As we can see, a chain reaction is being set up because we're getting a massive increase in the number of neutrons and nuclei. Figure 15 shows the inside of a nuclear reactor in a power station. So you've got hot water coming out, cold water going in, control rods. Obviously they're going to make it mean that it doesn't form a nuclear bomb because they help control the reaction. In a nuclear reactor, a chain reaction occurs which causes neutrons to be released. The control rods absorb neutrons. The control rods can be moved up and down. Explain how the energy released by the chain reaction is affected by moving the control rods. So clearly when the control rods are moving down, they're dipping into the nuclear reactor, which means neutrons will be absorbed, and therefore the energy released will be decreased because there's less neutrons going on and bombarding other uranium nuclei. So just write, lowering the control rods increases the number of neutrons absorbed, meaning that energy released decreases. Figure 17 shows the student before and after a bungee jump. The bungee cord has an unstretched length of 20 meters. The mass of the student is 50 kilograms. The gravitational field strength is 9.8. Write down the equation linking gravitational field strength, GPE, height and mass. So this is your equation, GPE, so gravitational potential energy equals mass times gravitational field strength times height. Calculate the change in GPE from the position where the student jumps to the point 20 meters below. So we're looking for GPE equals the mass of the student, which was 50, times gravitational field strength, which we were told is 9.8, times the height, which was 20. Pop that into your calculator and you'll get a value which is 9,800 joules. 80% of this change in gravitational potential energy has been transferred to the student's kinetic energy store. How much has the student's kinetic energy store increased after falling 20 meters? So you do that by calculating 80% of the number you've just worked out. So you do 80 over 100 times by, let's just look back up, that's 9,800. So when you pop that into your calculator, you'll get an answer which is 7,840 joules. Calculate the speed of the student after falling 20 meters. Give your answer to 2 sig fig. Don't forget to look back and check that you've done that. So your equation this time is kinetic energy equals half of mass times v squared. So we know kinetic energy is the number we've just calculated, which is 7,840, equals half times the mass, which was 50, times v squared, which is what we're after. So then simplify that down to 7,840 equals half of 50, which is 25 times v squared. How do you get v squared by itself? Well, divide both sides by 25. So you do 7,840 divided by 25 to get 313.6 equals v squared. And then in order to work out v, just square root that answer. Where's the square root sign on an iPhone? Oh, great. So please work. Okay, so the answer here will therefore be 18 meters per second, and that is to 2 significant figures.